Hello, in this video we're going to learn about exponential functions. Exponential functions are in the form y equals a times b to the x, where a cannot be 0, obviously, because if a were 0 then this whole thing would be 0, and we wouldn't be graphing anything. B has to be greater than 0, we can talk more about that later, and b cannot equal 1. If b is 1, then bringing it to different exponents won't matter because it'll always be 1, right? B to the first is 1, B to the second is 1, and so on. So let's go about graphing one of these functions first. Here's y equals 2 to the x. Notice it's following this form here where in this case a is just 1, right? It's not even shown. Basically it's like saying 1 times 2 to the x. So the a is 1, the b is 2, and the x is the x. So one thing we can do here is make a xy chart. So if x is 0, we know that 2 to the 0, or anything to the 0, is 1. If x is 1, then this is 2. If x is 2, then y is 4, 3, we get 8. So let's start by plotting these points. So 0, 1, 1, 2, 2, 4, and 3, 8. Okay. So as you can see, it's not linear, so it's going to be a curve. So when you graph this, don't connect them linearly. Got to make a curve. That's not perfect, but you get the idea. Alright, there we go. Now, some of you might be wondering, well, what happens when x is negative? Well, when x is negative, keep in mind that that just takes the reciprocal. So 2 to the negative 1 is 1/2. So when x is negative 1, y is 1/2. Not negative, positive 1/2. And when x is negative 2, 2 to the 2 squared is 4, so 2 to the negative 2 is 1/4. So that's even farther down. And notice if we put in like negative a million for x, it still won't dip below 0 because 1 over 2 to the million is still a positive number. And so what we end up with is a curve that kind of follows the x-axis here. So it never dips below, but kind of follows it forever. Gets closer and closer to the x-axis, but never actually touches it. Alright, so there is the graph of y equals 2 to the x. Alright, so now I'm going to graph y equals negative 2 to the x on the same graph just to show you what that looks like. Some of you may be thinking, well, this b is supposed to be greater than 0, so how are you able to do this? Well, the b is not being, the negative 2 is not being raised to the x power. Just the 2 is. This x only sees the 2. The negative is applied after. So everything's going to be negative. So you can really think of it as a negative 1 times 2 to the x. So in this case, the a is negative 1, the b is still 2, and the x is x. And so the same thing is going to happen as before, except everything's going to be negative. So we have 0, negative 1, 1, negative 2, 2, negative 4, 3, negative 8, and so on. I forgot to put the fractions over here. So negative 1 would be negative 1/2, and so on. And so what that looks like is it's just a mirror image here. That's 4. This one's 8. And so it looks something like, there we go. It's not perfect, but it's not too bad. And again, the green one will never go above the x-axis. And it looks something like that. It's pretty good. All right, let's take a look at some other functions here. Now, what if b, the b value, is a fraction? Let's try that. So, again, we can make an xy chart. If x is 0, y is 1. If x is 1, we have 1/2. If x is 2, we have 1/4. Okay, so you can tell it's going to get smaller and smaller as we go bigger on the x. So what happens when x is negative 1? Remember, a negative exponent takes the reciprocal, so that's going to be 2 to the first power. right? And if we do negative 2, it's 2 to the second power. If we do negative 3, it's 2 to the third power, and so on. So it's going to look the same, but in a different direction. So we have 0, 1, and then we have 1, 1/2, and it just gets smaller over here, and we go negative 1, 2, and so on this side, it kind of looks the same as it did over there. So it looks kind of the same, but in a different direction. Trying to make this as good as possible. Again, it won't dip below the x-axis. You'll just keep following it like so. And then the purple one is going to do the same thing. Everything is going to be the opposite, so it's going to end up looking upside down. So something like this. So we kind of follow, and again the line will never go above the x-axis, just kind of keeps following. Something like that. Alright, so we also have to identify linear and exponential functions. If you remember from a few chapters ago, we talked about a common difference. And so if we look at this chart here, notice the x's are just going up incrementally by ones. This first one is a change of -2, and then this one is a change of -6, and this one's a huge change of, I don't know, -18 or something. So that's definitely not a common difference. This one is a change of +2, +2, +2. So this is a common difference. Okay, so this is a linear equation. And then if it's not a linear equation, one other thing we can check is if it's an exponential function or exponential equation. And so in this case, we're trying to look for a ratio rather than a difference. And so -1 times 3 would be -3. -3 times 3 would be -9. -9 times 3 is -27. So this is a common ratio is what it's called, because we're not getting to the next number with addition or subtraction. We're doing it with multiplication or division, but multiplication in this case. And so this is exponential. And you can see how fast it grows or shrinks here, because we go from 3 to 9 to 27, and it'll just get much larger to 81, and so on. All right, let's try to solve a word problem here. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. The function f of x, which we all know means y, equals 30 times 2 to the x. So that function gives the population after x weeks. How many beetles will there be after 56 days? Well, 56 days, first of all, we need to turn that into weeks, so that's 8 weeks. So we have y equals 30 times 2 to the 8th power. 2 to the 8th power is 2, 4, 8, 16, 32, 64, 128, 256. So what we have is 30 times 256. So we're going to end up with a lot of beetles here. 256 times 3 is going to be, let's see, 750 plus 18, so 768. So we're going to end up with 7,680 beetles after 8 weeks. That's a lot of beetles. All right, so now we're going to try another one here. We're going to graph this. Again, we can make an XY chart. I forgot to pull a graph out. Here we go. All right. So when x is 0, we have 3, because 1 times 3. When x is 1, we're going to have 6. When x is 2, we're going to have 12. So that's probably off the graph already. So when x is not -1/2, let's make it -1. Then we'll have 3 times 1/2, so it's about 1.5. And if it's negative 2, it'll be 1/4, so about 3/4. All right, let's try to graph that. So 0, 3, about here, 1, 6, 2, 12. It's going to be off the graph a little bit, maybe up here. So negative 1, 1.5, about here. Negative 2, 3/4. That's going to be about here. So we get the idea. So try to make the curve as curvy as possible. I don't expect perfection here. But again, it's not going to go below the x-axis. Alright? Make sure to put your arrows there to show that it goes on forever and ever and ever. Alright, let's try another. So let's say we wanted to solve something that looks like this. Now we haven't learned to solve an equation where the variable is where the exponent is, and so I'm going to teach you a tricky way to go about doing this. Let's say we were to make two equations. So let's say we make an equation y equals this side. And let's say we were also going to make an equation where y equals the other side. Okay. Now if we graph both these equations, so y equals 2 to the x, we'll start with that. Let's see, so we'll start with negative 2, we get 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. I think we graphed this one earlier. So I'll graph this one. Negative 2, negative 1. No, negative 2, 1/4. Negative 1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. Something like this. Oops, I dipped too low there. There we go. Alright, and then up here. Now let's graph the green one. That one should be a lot easier because it's in slope-intercept form. So we start at the 2. Then this is a 1/2, right? 1/2 x plus 2. So that's up 1, right 2. Up 1, right 2. And so it looks something like, let me get my line here. Something like that. Now if we check to see where these intersect, and so it looks like the x value of this intersection here is almost 2. Now my graph might not be great, so we could say x equals or almost equals 2, probably less than 2. And then over here again my graph is kind of messed up, but I'm going to say it equals something near negative 4. Okay. So when we're trying to solve something like this, it's just an estimation. But what we can do is use a graphing calculator. So let me see if I have that set up here. I do. So here's a graphing calculator. And what we can do is enter those equations that we entered. Y equals 2, and we need this little caret symbol here, and then x means 2 to the power x. And then our other equation was y equals 0.5x plus 2, so 0.5x plus 2, and then we can graph that. And then this graphing calculator here shows intersections, so you can see that our graph looked pretty much the same as the one on here, and we can graph the intersection, so find intersection points for both the equations. And remember, we only care about the x value, and so it was negative 3.8 and 1.44. So let's see what we came up with here. So we had negative 4, so that was pretty close because the actual was negative 3.88, and then on the other one we had 1.44. So we were kind of in the area. So that's how you can solve an equation like that. And thanks for watching.